second year that we have actually this AI and data talk series. We are starting with the first presentation and an excellent presentation with the title Data-Driven Models in Predictive Control. And more specifically, we're talking about uncertainty quantification, and robust designs. So the talk is given by Johannes Köhler, who's Dr. Johannes Köhler, who is an assistant professor in the Department of Mechanical Engineering at Imperial College. He received a PhD degree from the University of Stuttgart, Germany in 2021. And from 21 to 25, he was a postdoctoral researcher at ETHZ Zurich in Switzerland. He has received several awards for his work on control theory, including the 2021 European Systems and Control PhD Thesis Award, the IEEE CSS George Axelby Outstanding Paper Award in 2022, and the Journal of Process Control Paper Award in 2023. So the research of Dr. Johannes is related or focused on the control of autonomous systems, bridging the gap between rigorous theoretical guarantees and applications. So welcome actually Dr. Johannes with us actually for this, our first talk in the second year of our AI and data talk series. So the floor is yours, you can start. And let's actually, guys, we leave the questions at the end. You can type in the questions in the chat. We can take them from there. Or if you want to ask your question directly to Dr. Johannes, please feel free at the end of the talk. Thank you. Please, Johannes.
Thanks a lot for the introduction. And it's my pleasure to be here today. As already mentioned, I'll talk today about predictive control. And specifically, I want to focus on when we talk about data-driven predictive control, that really uncertainty quantification and robust designs are the key elements we need. Before we jump too much into details, let's start with some high-level motivation, starting from the kind of applications I'm typically thinking of. So I'm typically looking at robotics types problems like robotic manipulators, autonomous drones, deformable robots. And if we think about what we want to achieve, typically here we want to have autonomous systems. That means they can also do high-level decision making. They can move autonomously. We want to deploy these systems in safety critical scenarios. That means there can be obstacles, there can even be humans, and we really want to be sure that these systems operate the way we want them. And we often have a lot of physical behavior in these systems that are difficult to model, especially if you, for example, think about a deformable robot, but also for a lot of these other problems. And on a very high level, what we really want, or what's the goal of this talk, is to think about how can we get a reliable controller from data in automated fashion. So I really want you to think about having experimental data, executing a Python script, and getting a controller that you're confident in applying to the real system. Now, what makes these problems challenging? So one thing I already mentioned is we want safety critical constraints. That's important. There's also a lot of things that are uncertain about a system behavior. There's external noise we have to think about. And there's also the fact that typically we don't know how big these uncertainties are or how our actual system model is. And the answer to these questions that I'll present in this talk is what I call data to predictive control, short D2PC. And we'll have later some illustration that explains this better. But in essence, we want to use the experimental data we have to characterize both a model that explains the data and an uncertainty description. Then we want to use this description to design robust controllers and predictive controllers. And by combining these elements, we'll get a data-driven control design that will give us desirable performance and safety guarantees. Now, the overall work, we can think about the following pipeline. And also all of this presentation will be based on this pipeline. we start with a real system for which we do an experiment and we get input-output data out of it. Usually it's noisy. Then we have structural constraints. By this I mean prior knowledge we have about the physical system. Whatever we have, we want to be able to use it. That's also a very important property. Then we combine our structural knowledge with the data in estimation step to get as much information from data as we can about our physical system. In a second step, we want to do uncertainty quantification. So we want to get an understanding of how accurate our model is that we retrieve from data. Once we have our model and a description of the uncertainty, we want to do a robust control design where we want to be sure that we account for these model uncertainties. And in the last step, we want to also use a predictive control with online optimization during runtime, which will additionally enforce safety critical constraints for the uncertain system. So if we think about designing such a control design, if we think about such a control design, it touches actually about different research fields in the control theory. The first one is the field of systematification. Classically in systematification, we think about how can we retrieve models from data. Sometimes we also think about uncertainty quantification there, so how accurate are models. But typically systematification does not deal with the separate control synthesis based on the model. Another related field is the field of robust control. In robust control, we're given typically uncertain models, often with a block structure like this, and we're able to synthesize controllers that give us stability and performance guarantees for this uncertain system. But this field of robust control typically cannot account for the constraints we have in physical systems, such as actuator limitations or obstacle avoidance. Now, the third related research is model predictive control. In model predictive control, we try to enforce constraint satisfaction, so actuator limitations and obstacle avoidance. But typically, most of the model predictive control theory requires an accurate model for predictions and also assumes state measurements. So we see if we want to have such a data-driven design, we need tools from all of those three disciplines, and we see that none of those three research fields actually answers all of the questions we need. So really what data predictive control aims to do is to get the best out of those three fields to be able to put them together. And the key challenge here is the fact that these different research fields in control have inconsistent modeling assumptions. What do I mean by that? If we look at systematification, classically, we assume that we have stochastic, often also Gaussian, process and measurement noise, which is IID distributed. On the other hand, if we look at the field of robust control, there we typically deal with uncertainties that are dynamic functions which live in some deterministic set that we know. On the other hand, if we look at model predictive control, we typically assume that we measure the state, and often we don't have any model mismatch or very simple description of the model mismatch, for example, that simply lives in a compact set like a polytope. So you see, really, we have here three very different descriptions of uncertainty, so it's hard to just combine those fields. And one of the key technical contributions we've made to be able to combine them is that we derived robust control methods and predictive control methods that are tailored to the uncertainty that is compatible and resulting from the systematification step. Now, one thing I want to note, throughout this talk, I will mainly look at linear dynamical systems. This will make a lot of the exposition easier. And towards the end, I'll briefly touch upon what results we currently have for nonlinear systems and what is still challenging. So what we'll look at here in this talk are linear stochastic systems, where here X is the state, U is the control input, W is the process noise, Y is X plus is the next state, we'll do here discrete time, Y is the measurements we receive, which are partial measurements of the state, plus measurement noise. And we assume that the process and measurement noise here are Gaussian distributed IID with some covariance matrices Q and R. Now what's important is the system matrices A and B and the noise magnitude given by its covariance matrices Q and R are not known a priori. Instead, what we have is an input-output trajectory obtained from an open-loop experiment of a finite length. So what we have to do is first we have to go from this data to means to estimate these unknown quantities. Then to also get safety and reliability guarantees, we need to understand how big the epistemic and aleatoric uncertainty is. And here's a reminder, aleatoric uncertainty means the stochastic uncertainty that's just in nature, so process noise and measurement noise. And epistemic uncertainty is the uncertainty to limited knowledge. So because we don't know the exact entries of the A and B matrix, for example. So we need to understand how big those two uncertainties are. And then we separately need robust and stochastic predictions methods that can account for this uncertainty. So this whole talk the outline of this talk will be based on this pipeline. And now that we've described the real system behavior, the first step will be understanding the estimation step, where we've given this noisy data, and we'll talk about structural knowledge that we can optionally incorporate if we have it, and the type of estimation procedure we do. Now, the structural constraint we'll assume here is that the A and B matrix, which we don't know, are linearly parameterized by an unknown vector, which is finite dimensional. So what does it mean? If we don't know anything about a system, modulo maybe an upper bound on the order, then we can take a normal form, like an observer normal form, where we know certain entries will be 0 or 1, and all the other entries that we don't know will be given by this finite dimensional parameter. On the other hand, if we have a physical system, like a mass spring damper system, and we just don't know the damping constant, then only this one entry parameter, which we don't know, will be given by this uncertain parameter. And by just saying these matrices are affinely parameterized, we can model flexible combinations of these two. So whatever prior knowledge we have, we can incorporate. In addition, for the covariance matrices, we assume they are also parameterized, not necessarily affine, by some vector. This can, for example, be diagonal or Cholesky decomposition. What's important, everything we don't know about a system can be captured by this finite dimensional parameter vector theta. Now, what we do for estimation, in some sense, is very simple and classical. We do maximum likelihood estimation. That is, given the data we've observed, we look at the likelihood of a certain parameter, and we search for the parameter that's most likely given the data. Now, what's important to note, even though the dynamics are linear, the maximum likelihood estimation problem has no closed form solution. And the reason for that is both the model parameters, but also the internal states are unknown. If the state would be measured, this would be a very simple problem. So how do we solve the maximum likelihood problem? We resort to the expectation maximization algorithm. This is an iterative algorithm that iterates two simple steps that will converge to a stationary point of the maximum likelihood problem. Specifically, in the E step, we'll consider a given model parameter, theta, and estimate the state distribution, assuming this parameter is correct. And for a linear system, this just means running a Kalman smoother once over the data, giving a posterior covariance distribution of the state. Once we have this distribution of the state, we'll maximize the likelihood of the parameter conditioned on this distribution. This M step is often a simple least squares, depending on the exact parameterization of the system. What one can show, if we iterate between these two steps, the likelihood will monotonically increase and will converge to a stationary point. And what's important, this remains true if we use a so-called constrained M step. So this is also true if here in the parameter we have very strong parameterization of the A and B matrix, and we don't have to treat every element as unknown. And this is very important to get sample efficiency. Okay, so what does it mean? If we execute the step, then we'll get an estimate of the model parameters and an estimate of the process and measurement noise covariance matrices from data. And we can do this for stochastic input-output data and for structured models that are affinely parameterized. Okay, so with this we have an estimate of our system, And next step, we want to do uncertainty quantification. So we want to know how accurate this is. And here, the key point we have to watch out for is there will, in general, be a mismatch between the parameters we estimated and the true parameters given by the finite data and the stochastic noise. What we leverage here is that under certain conditions that I'll specify in a second, the maximum likelihood estimator, the error resulting from the maximum likelihood estimation is asymptotically Gaussian distributed. So what I mean by that is the difference between the real parameters in our estimate follow a Gaussian distribution, and the covariance of this distribution is given by the Hessian of the necklog likelihood. And this is something we can evaluate. So we can evaluate a covariance matrix that describes our uncertainty about the parameters, and with this we can build a confidence set that contains the true parameters with a desired probability using the chi-square distribution. So this will be an ellipsoidal set. Let me say something about this asterisk here. So what's important is this guarantee first requires some structural assumptions, in particular identifiability. Typically, it also requires a suitable parameterization, persistently exciting data. And the other more important restriction is it in general only holds asymptotically. So we need a lot of data points for this approximation to be true. If we have very few data points, in general, the error will not be Gaussian distributed. The following will assume that this approximation is valid or it's a good enough approximation. If we do this, what we get is from a step before, we already have an estimate of the aleatoric uncertainty by the noise covariance matrices for the process and measurement noise. We'll not treat the uncertainty in those here because they are less relevant for the kind of applications we look at, but there are also ways to do this. In addition, we have an epistemic, the description of the epistemic uncertainty given by a deterministic ellipsoidal set on these parameters that are uncertain. Okay. Now that we have an understanding of the model and a description of the uncertainty, we'll go to a robust control design. And here, the goal will be to design an output feedback controller because we only have access to output measurements that should stabilize the true system and in general be optimal according to some criteria. And for simplicity, we look here at the H2 norm minimization, but this can be generalized to, for example, minimize a peak norm for minimizing constraint violations. And the picture we want to have in mind is this block diagram. We have our model, which is in a feedback loop with the controller we'll design, which has only access to output measurements. There are exogenous disturbances. This is both the process noise and the measurement noise. There is a performance channel we care about. This is typically variables we would like to track, directions in which we have constraints. But also, the model is not the true system. In fact, the model is in a feedback interconnection with an uncertainty delta, and it's only this feedback interconnection that describes the real system. And this type of a description is typically called a linear fractional representation that we'll look at. If we have a model and a system in this specifically linear fractional representation, then there exist many robust control synthesis tools that we can use that iterate convex optimization problems in the forms of linear matrix inequalities to get a robust output feedback controller. The challenge we have is these existing methods require a very specific description of the uncertainty in this linear fractional representation and a very specific structure of this uncertainty block delta. Instead, what we have is we have a finely parameterized model where this parameter is subject to a structured ellipsoidal constraint. Now, one of the key contributions here is we've shown an equivalent way to bridge these two descriptions. Specifically, let's just focus on the A system matrix. We can write the uncertain A matrix, which depends on the parameters we don't know exactly, as our nominal estimate from data, a matrix delta, which is the error in the parameters with a canonical product and an identity. So this is a very structured matrix, multiplied by a matrix which captures how the parameters finally enter the A matrix. So those matrices are all known, and it's only this delta matrix which is not known, which depends in a specific structure on our uncertain parameters. Now, what we've shown is the fact that the parameters lie in a given ellipsoidal set is equivalent to the fact that this matrix with this chronicle structure lies in the following uncertainty set. What's important about this description, if you've seen this before, we have here a matrix inequality on the matrix delta, and this is exactly the kind of description we need to apply existing robust control tools. Here we also have so-called multipliers, and here these multipliers capture the exact shape of our uncertainty, where we have here again this chronicle type structure, and here this matrix sigma captures the exact shape of the Hessian of the necklog likelihood, which we used for uncertainty quantification. What's important with this description, we can directly use existing robust control synthesis tools. In this case, we use the so-called full block S procedure. And by solving a sequence of convex optimization problem, we get an output feedback controller which guarantees stability and minimizes, in this case, the H2 norm for our uncertain system. Okay, so with this, we already achieved a lot. We now have a controller that stabilizes the system, guarantees some performance, but now we also want predictive control to deal with these higher level objectives, such as constraints. So here specifically, we want to have a predictive controller that, in addition, satisfies probabilistic constraints of this form. So why do we look at probabilistic constraints? We have stochastic noise, so ensuring deterministic constraints would not be feasible. These are half-space constraints, so this is the simplest form of constraints we can have. We can similarly look at input constraints, but I'll keep it simple here. And we want that these constraints at any point in time are satisfied with a certain probability P, which the user chooses. And we want to be sure that these probabilistic constraints hold for the closed loop system, even though we don't know the exact model parameters, and we have unbounded stochastic process and measurement noise, and we only have access to output measurements. The key challenge is that the prediction of the future state depends on this unknown deterministic parameter and on this unbounded stochastic noise. How do we deal with this? If we would know the model exactly, then we would see that the future state also follows a Gaussian distribution where both the mean and the covariance depend on the uncertain model parameter. Now what we do is we treat both of them independently. Offline, independent of the actions of the controller, we can do a stochastic propagation where we compute a covariance matrix, which is a robust upper bound, to the future covariance matrix, which we do not know. This can be done with a semi-definite program and is very similar to classical robust control tools. What's important, I'm talking here always about Gaussian distributions, but most of the things I'll present in the following equally work for so-called sub-Gaussian distribution, which is a more general class of noise distributions, which doesn't just include Gaussian distributions, but also, for example, uniform distributions and any zero mean bounded distribution. So we deal with the covariance matrix by computing offline a fixed bound. Now for the mean, it's a bit trickier because the mean error depends on the actions we take. So what we do here is we use a deterministic tube propagation. Let's first look at the figure. If we have a given initial condition and a certain plan we would like to execute, then for different system matrices A, we'll get different predictions. What we want is we want to predict a sequence of sets, in this case ellipsoids, which capture all these possible futures. First, we need to choose a parameterization of these sets. Here we pick ellipsoidal sets that are centered around some nominal prediction and that are scaled by some scaling alpha. And now we just have to determine how much do we have to scale these ellipsoidal sets to make sure all the uncertain trajectories lie within it. The way we determine the scaling is this simple scalar error propagation. This says the scaling at the next time step is first exponentially contracting. This means if there's no uncertainty, the uncertainty would shrink over the horizon because we designed a robust controller that's stabilizing. But in addition, we excite elements of the system where we are uncertain about the future. This is captured by this term. I will not provide the closed form expression for this because it's a very long expression, but it's a fixed matrix we can compute offline. And this captures exactly how a state how the parameterization of the model and how the uncertainty parameters interact. And it just tells us how uncertain are we of the system response at a given state and input. By combining all of these elements, we can derive a model predictive control formulations. Before we go through the math here, let me explain what we see. The first important point to note is the way we'll derive an MPC formulation is that we'll integrate the robust controller we designed offline in the MPC. That is, in the prediction, we'll have here an augmented system that doesn't just simulate the model, it simulates the model and the dynamic output feedback controller together. Because we already designed this robust controller and we would like to implement it. In addition, the way we set up the model predictive controller is that the input we'll apply will be the linear dynamic output feedback controller plus an additional input nu. And the MPC only optimizes how much we deviate from this offline computed controller. And this deviation will be penalized in the cost. This means, if possible, our MPC scheme will always try to simply apply the offline computed linear controller. Why do we deviate? The only reason we deviate from the offline computed linear controller is to satisfy the probabilistic constraints. These are enforced with a tightened constraint here, which uses a term accounting for the stochastic noise and a term accounting for the deterministic uncertainty, where the scaling alpha we've seen before is propagated in the system dynamics. And note that this can be implemented as a second-order cone constraint. In addition, we have a standard sum set constraint, and as an initial condition, we'll simply use the previous prediction. With this formulation, we can get quite strong theoretical guarantees. But let me first summarize the conditions again. In the following, I'll assume first that the uncertainty description we got from data is correct. That means the real process and measurement noise has a covariance that's equal or smaller than the estimates we got from data. Secondly, the parameter set we captured from data contains the true parameter. Furthermore, we have to assume that this optimization problem is feasible when we start a system. Under these conditions, we have three guarantees, which are in general all the guarantees we'd like to have. First, we have that the closed loop system ensures recursive feasibility. That means every time step when we try to solve our MPC problem, it will be feasible. Secondly, for the closed loop system, the chance constraints will be satisfied. What does it mean? It means if I start 1,000,000 simulations for different initial conditions and I run all of them, and at any given point in time I check if the constraints are violated, then 99% of these simulations will satisfy the constraints, assuming I set here 99%. Lastly, we get a performance bound. Performance bound we get here in the limit, and here we write the limit for simplicity. We can also write transient bounds. The average quadratic cost is bounded by some constant gamma squared. This gamma squared is the H2 performance bound we optimize the robust controller offline. This simply means in the long run, the performance in terms of the quadratic cost we chose here of the model predictive controller will be as good as simply running the unconstrained linear robust output feedback controller. So this means we inherit the performance instability from the offline design robust controller, while the online optimization accounts for stochastic noise and uncertain parameters and ensures satisfaction of the probabilistic safety constraints. Let me provide a simple example to illustrate some of these properties. This is a chain of mass spring damper system, 10 states, 5 inputs, 5 outputs. So we just measure each of these positions. We'll assume here we know the structure of the model. That means we know which entries are 0 and not. And this gives us 23 uncertain model parameters for this problem. So if we take here 2,000 data points from one simulation, and we run this algorithm to estimate the model and the magnitude of the noise, it takes about 6 seconds. Then for the uncertainty quantification, I mentioned it's asymptotically correct. And in fact, what we get here, if we run multiple tries, the real parameter will lie in the set we computed from data with 49.9%. while in reality we try to have 95%. So we see there's an offset, but it's quite small in my opinion. Then we do this robust control design, which is this full block S procedure, which takes about 6 seconds. Then online, we solve this model predictive controller, which takes about 29 milliseconds every time step. On the right, we can see some results. We have here some starting position and we have a position change. This shaded area is all the uncertainty, so different realizations of the noise. And here we have the velocity, and here we have a constraint on the velocity we'd like to keep. What we see here, the sum of the trajectories violate the constraints because we only specified a certain probability to satisfy them. What's important here is wanted to have at most 5% violations, and we have at most 2% violation. So this means we have sufficient conditions, but they are slightly conservative. But I would say it's not too bad. What's more important than the results, in my opinion, is the pragmatic aspect. Executing this pipeline for this 10-state model was completely automated. You just say rough structure, you compute a Python script, and now in 12 seconds, you have a controller that you can directly implement, which is reliable, stable, gives you performance and safety guarantees. And we have open source implementation of that, and it's coded in a generic way, so that for similar problems, you can directly apply it. Very briefly, I want to mention there are other approaches in literature, and there are many approaches that are called direct data-driven approaches. And we want to compare to one of them, here specifically the approach by Unidine. What's important, what I've presented here is a modular pipeline that has multiple steps. This has many benefits in my opinion. We can exchange different modules, we can replace the robust controller with a different robust controller, but it also means we have to execute these multiple steps. In addition, it may look not as easy because we have to deal with the state estimation. These direct data-driven approaches often try to circumvent a lot of these problems. One way this is done is that instead of dealing with state estimation, a lot of these approaches take a window of past input-output data to replace the state estimate. This makes it a lot easier to apply. And the following will compare to one of those approaches. I should mention here, this competing approach is given access to exact measurements of the process noise because this was necessary to implement it, and otherwise it was not possible to compare at all, but we're still better, which is why it was fine. Let me walk you through the results. Let's first look at the right. What we see is the level of constraint tightening necessary to guarantee safety. And this is normalized to 1, where 1 is the tightening we would need if we know everything perfectly about a system. And what we see here in blue is this direct approach for different length of past window used to replace the state estimator. And we see if we take a small scale model like 20, 30 states, we're like 100 times worse than the perfect model. But if we increase the state dimension a lot to here 100, 150 states, we get a lot better. We're still maybe factor 6, 7 worse, but we get in a good range, I would say. In comparison, the proposed approach, D2PC, we can see here we're a lot closer. We're still more conservative than perfect model knowledge, of course, but we're a lot better than these direct approaches. What's even more important, in my opinion, from a practical perspective, to achieve this good performance, these approaches need to use a long window of past input-output data, which gives a large dimensional state space, which will give me large optimization problems, both offline and online. We can see this here in this table. The proposed approach, D2PC, online solving the MPC problem, which is a second-order cone problem, requires about 20 milliseconds. In comparison, these direct approaches here, with these large state dimensions, require about a second, so 50 times longer. And this is even for this moderately scaled problem. So what's the message I want to give here? We have a modular approach which can use compact and structured state space models. This has drawbacks. The estimation is harder. We had to look at what algorithms to use. But the benefits we get from that is not just that we are less conservative, we can use more prior knowledge, but we're also more computationally efficient when applying it online. Okay. This is the main part I wanted to cover. I want to just quickly give you a flavor of what changes if we go to nonlinear systems. And this means if we do the same pipeline, but for nonlinear systems, why does it get hard and what can we still do? And here the key challenge, in my opinion, is the data-driven estimation. And the problem is what we used so far is that the maximum likelihood estimation or the state distribution has a closed form solution like a Gaussian distribution. And this breaks in a nonlinear setting. What we can do instead, we can use moving horizon estimation to provide a finite horizon recursive approximation of the maximum likelihood estimation for a given model. Now, how can this help us? The way we can identify models from data instead is we can identify parameterized models using the so-called classical prediction error method, where we just train a predictor from data to be as good as possible. And the trick here is that we can use moving horizon estimation as a general state estimator for general nonlinear dynamics. In addition, for uncertainty estimation, we can also use moving horizon estimation to estimate the magnitude of the process noise and measurement noise from data, which can then be used to determine the maximum noise we need to account for in the robust design. For the robust and predictive control, the first thing I have to note is that model predictive control on its own is very well suitable for nonlinear systems. There are strong theoretical results, there are good numerical solvers for nonlinear systems. What is harder is the robust or stochastic design for nonlinear systems, because there's no exact formula for uncertainty propagation. One of the solutions to this problem are contraction metrics. They provide a systematic method to extend analysis and synthesis tools from linear to nonlinear systems, including some of the robust control tools we've seen before. What we can do with this, we can enable the robust and stochastic prediction error bounds for nonlinear systems, and by embedding them in a model predictive controller, we can get robust or probabilistic guarantees for our nonlinear systems for a given description of the uncertainty. So this is just to say, in recent years, there's been also much progress to address these challenges for nonlinear systems, but they're by far not as mature as the linear case. I just want to show one example also for the nonlinear case. What we have, this is joint work with TU Delft. What we have here is we have the rotor S model from Gazebo. This is a physics simulator of a drone. And on the other hand, we take now a known model as our model as standard 15-state nonlinear drone model. We'll assume we have a rough idea of the magnitude of the noise, but there will be a structural mismatch between those two models. And we want to estimate it from data such that we can automatically design a robust controller. Now what we do is running this moving horizon estimation offline over a large period of data requires about 1 hour here for these experiments. Then we use this understanding of how big the noise is to design a robust controller, which takes about 5 minutes. We take another calibration flight for different reasons, and with this we get a reasonable error quantification. We can see here on the right, for example, the error for a closed loop simulation with a stabilizing feedback. And here in blue, we can see our computed bound on this error, which follows a stable first order system behavior. And what's important, this is similarly a modular open source pipeline. And by executing it, doing 2 flights, we have a reliable controller after 2 hours. And of course, 2 hours is a lot longer than the few seconds we said before. But if you work with real robotics problems, having something that runs after 2 hours is really good, in my opinion. Yeah, this already brings me to the conclusion of this talk. I've presented an automatic design pipeline where we go from data to estimation, uncertainty quantification, robust control, and predictive control. What's really important is this pipeline is modular. It applies to stochastic input-output data. And the key novelty to realize it is that we develop robust and predictive control methods that are tailored to the uncertainty characterization we get from data. What I present today is largely based on this paper, which was led by Haldun Balim, who was a previous student of mine. In my opinion, the methodology is quite mature now. So for certain classes of problems, linear, not huge dimensions, I think you can really apply this out of the box. With this, I want to thank you for attention, and I'm looking forward to some questions.
Thank you very much, Johannes. So guys, I'm happy actually Johannes will be happy to receive your questions. If you have any question, put it in the chat or maybe raise your hand. I see actually already one hand. Van Katraman, I think actually, please go ahead and ask your question.
Thank you so much, Johannes, for the fantastic talk. First of all, so I have two questions to actually ask you. So can you go to slide number 18? Yeah. So essentially, you have like an upper bound on the covariance, right? So because what I see here is that once you have the controller from the robust control design, and what you want to do is just actually handle the uncertainties, you can pretty much do something like a simple covariance steering, right? Because when you do a covariance steering, you will have a similar terminal covariance constraint. You can handle both state and input constraints in a probabilistic sense, meaning that you can do a chance constraints for both what you call uh, the satisfaction of both state and input constraints in the probabilistic sense. And if you go to equation 20, what happens, slide 20, what happens is that, yeah, this will allow you to actually also do some sort of a risk allocation across time step, because you are actually enforcing the same risk across all time step. And that will actually, because I see some sort of a tension between satisfaction of the chance constraint and the satisfaction of the performance, the H2 norm bound. So
What
I
is the
feel like you
question?
can reduce the conservatism a little bit. So can you
Thanks for
give
the
me?
question. I think so. One question was probabilistic constraint versus risk allocation. And yeah, we use probabilistic constraints because it's the simplest thing here. We want to have the full pipeline. I don't think anything would prevent us from doing risk allocation instead.
Yeah.
But maybe what's important if we contrast to, let's say, covariance steering. So here the policy is largely already fixed. So we have a structured dynamic output feedback controller compute offline. We only online optimize an input sequence. But what's the challenge is that we don't know the model. Most covariance steering problems I know have a known A and B matrix. And the reason we compute a upper bound and not just know the covariance is because the A matrix, the B matrix have a very structured uncertainty that we don't know exactly.
Okay.
This is your second question, Venkataraman?
Yeah, and just one more question. Like, so you said like your estimator is asymptotically Gaussian in the one of the first two slides, right? Yeah, here, especially. Can you use some sort of new methodologies like conformal prediction with finite data to come up with that set theta, capital theta? Because all you have is just t times the finite time input output data, right? Can you construct a confidence set using the conformal prediction to answer this?
Good question. So yeah, so relaxing the asymptotic aspect here would be nice. There are different finite data points. There are a lot of classical finite data points in SysID. If
Yeah.
I measure the state, that would make it easy, but I'll look at problems where I don't measure the state. Conformal predictions would have a very different interpretation of the probabilistic validity. I think that's important to keep in mind. And I would still say I would not be able to apply it because it would not be straightforward to apply conformal predictions here to get this error bound.
Yeah. Thanks.
Okay, thank you. Any other question, guys, please? Please come forward for any other question. Yes, Owen, please go ahead.
Hi. Yeah, this is not really my area, so I just had a kind of like a high level question following on about this like contraction theory and conformal prediction. What would you say is like, would you be able to give like a sort of like a high level comparison maybe between like the advantages and disadvantages of your method compared to something like a conformally contracting controller. Because my understanding is that you can also get bounds like on the sets for your controller in that case, and like yeah, are you able to provide sort of like a high level comparison between the two?
But just can you be clear? So you said multiples, you said conformal predictions, you said contraction metrics. Do you mean, which one do you mean? Or
So in the case that you like some recent work on like conformally contracting controllers. So like there's a paper by Hiro Tsukamoto on this that I just came across recently where they can like combine conformal prediction and a contraction metric to come up with a controller.
okay, okay, I think maybe on a high level, a lot of what this talk was about is understanding model and uncertainty from data. And once I have it, for linear systems, I know how to design a good controller. For nonlinear systems, that is contraction metrics. I kind of know how to do it, but it's actually sometimes a bit harder, I would say. It can be hard. And I hope I'm thinking of the right paper right now, but what you can do is you could also, with state measurement, nonlinear dynamics, for example, directly verify such contraction properties from data with conformal predictions. But this is just as because the nonlinear synthesis step is computationally challenging, you go to sampling. This is kind of more it. And by here for linear systems, I know how to do the synthesis. We have very classical tools. It's more the step before I do the synthesis, getting the model and some description from data which is usually there already given.
Yeah. Okay. So is it also that in this case it's quite a powerful thing that you don't assume you have any state measurements as well? This is
Yes. So I would really say if I would have state measurements, a lot of the things would get trivial. Like for example, systemification, a linear system with state measurement is least squares. I mean, yeah. And finite data bounds, there are a lot of papers that give you very good finite data bounds. Even for nonlinear systems, state measurements, I get very strong finite data bounds. It's really, in my opinion, once you go to experiments, you don't have state measurements. Even if you have, at best, you have noisy state measurements, usually not even that. And I think there's a big gap between some of the theory that exists that need state measurements for data-driven, while in reality, data is usually only output measurements. And this is where really it's hard.
Yeah. Okay, great. Thank you very much. That's very helpful. Thanks.
Okay, thank you. Any other question, guys? So if there is any last question, we take and then.
There's just one in the chat there, Nabil.
Okay. Can you maybe elaborate more about how to compute the factor row for the tube scaling example on the slide 18? That's a question for you, Johannes.
So in general, I would say robust MPC, one way to do robust MPC are these tube scalings with a contraction factor row. The best way is there's a way to automate it. It's called the peak gain. So you want to have the smallest possible tube. You optimize over this row essentially with a bisection to get the smallest tube. This is it. So it doesn't have an analytical formula. It's scalar. You do a bisection. You try to get the one which gives you the smallest tube. And in classic robust control, a lot of the literature is called reachability analysis and peak-to-peak gain.
Okay, so that's actually the answer. Okay, is there somebody else? Yes, Venkatraman. So last question, please.
Just wanted to have one more question.
Yes,
so
please.
I know your MPC structure that you showed in the 20. So is it possible that you have like a learning based MPC where you have an estimate? So in learning based MPC, which is fairly done, you have a nominal model which actually you can combine whatever you get it in the robust control. You have a nominal model and then you estimate the uncertainties from the data. Let's say you have using least squares, and you have a learned model. You use the learned model for the cost function, nominal model for the constraint tightening, something like a learning based MPC instead of just a robust MPC here. Because I want to get rid of, I mean, I don't know that your main purpose of using robust control is just to have a H2 bound, right? Instead, you can actually borrow those constraints into the MPC and then have the formulation of the MPC as a learning based MPC.
Answer conceptually, I can do a lot of learning based MPC also here. Practically, the systemification is a lot harder here because we don't have state measurement. So a lot of the strong online learning and adaptation methods for models are also hard. If I had state measurements, I would have a lot of methods. I would directly throw it also for nonlinear systems to online adapt the model and use these adapted models. It's in the output feedback setting that it gets tricky. And you'd first have to think about how you online quickly re-identify, learn your models in the input-output setting.
Okay. Yeah.
Okay, thank you very much. So thank you for the audience. Thank you actually, Dr. Johannes Köhler for the presentation and the answering the questions. Very great to have you here in this talk. So guys, actually you can have, I think this is a recorded talk, will be actually on our ACE YouTube channel. So please feel free actually to check it or provide actually link to your colleagues. So maybe actually they will be interested with this talk. Thank you very much, Johannes. Thank you for your talk.
Thank you for having me. And thanks for the questions,
Thank
everyone.
you.
Take care, guys. Bye-bye.
Bye.